Okay, now we move to the chapter 7 about the control charts for attributes. Let me choose the color of the cursor. Okay, there you go. So learning objectives of chapter 7 is try to understand the statistical basis of attributes control chart. So AKA, those variables are considered categorical or attribute type variables. So it can be in contrast with the comparison between the digital and the analog in digital transformation process, and know how to design attributes control charts, and know how to set up and use a P chart. P is a proportional for fractional fraction non-conforming, and know how to set up and use the NP. This is the number of defective item control chart for the number of non-conforming items. Know how to set up and use the C charts for defects. So how many defects exist in a single item or single opportunity, and know how to set up and use a U chart, U control chart for defects per unit. So actually, this is so the C is corresponding to a sample. The sample consists of the multiple observation. However, for the corresponding U chart, that is used to denote what is the average number of defects per unit of item, per unit of the product, per unit of the device, and so on and so forth. Use attributes control chart for variable sample size. If the sample size varies from lot to lot, so is any possible or potential way to do with the time varying sample sizes? Then understand the advantages and the disadvantages of attributes versus variable control charts. To understand the rational subgroup concept for attributes control chart. The last one, determine the average run length for attribute control chart. However, it is seldom discussed in the literature. Okay, control chart for fraction non-conforming. Spare some time. I would like to a cup of the tea. Then fractional non-conforming is defined as the ratio of the number of non-conforming items in a population. Population is a really large base size to the total number of items in that population. So the items may have several quality characteristics. In DMAC is known as the CTQ, critical to quality, that are examined and investigated simultaneously by the inspector. If the item does not conform to standard, one or more of these characteristics, and then it is classified as a non-conforming, or now it's a process fallout. And we usually express the fraction non-conforming as a decimal representation, although occasionally the percentage non-conforming, which is simply represented in the percentage times the fraction non-conforming is typically used. Then when demonstrating or displaying the control chart to production personnel or presenting results to the top management, the percentage conforming is frequently used as it has a more intuitive appeal. So sometimes if it uses a decimal point as a representation, it is not that intuitive to top management. Hello, so strange. So many organizations operate a yield management system at each stage of their manufacturing or fulfillment process with the first pass yield. If the first pass yield doesn't pass, so going to perform the second pass yield test, track on the control chart. Yeah, so strange. The alarm of the hotel. So it's under investigation. However, they didn't advise us how to deal with that. The statistical principles underlying the control chart for fraction non-conforming are based on the binomial distribution. I stop here for a while. I come back later. I call the front desk to check what is a test for the alarm. No. Sorry about that. I will be back in a minute. I check the long test. Oh. So I heard the hotel broadcasting the alarm investigation. What should I react to this? All right, all right. Okay, thank you. So the hotel telling us we should stand by for further instruction. That's strange. Okay, back to here. So maybe some sensor is broken. Then the statistical principles and underlying the control chart for fraction non-conforming are based on the binomial distribution. Suppose that, and the production process is operating in a stable manner called statistical process control, such that the probability that any unit will not conform to specification is denoted by P. So that successive units produced are independent. So this is based upon the assumption of Bernoulli trials. So if a random sample of n item of product is selected, if the D is a number of units of product that are non-conforming in a sample, then D has a binomial. D will follow a binomial distribution random variable with parameter n and p. Correspondingly, that represent as equation 7.1. So from the previous chapter 3, we know that the mean and the variance of the random variable D are NP and NPQ respectively. So the sample fraction non-conforming is defined as a ratio of the number of non-conforming units in the sample D to the sample size n. So we do we compute the ratio D over n as estimate P. We put the caret on the top of the P. As noted in chapter 3, the distribution of the random variable P hat can be obtained from the binomial distribution. And moreover, the mean and the variance of the P hat can be calculated corresponding to the P. P minus 1 things divide by P, this is X by P, origin NPQ. So this is a PQ, this PQ. So this is NP, this is NPQ, and PQ, and divide by, this is, I'm sorry, this is N, divide by N squared. Finally, the N cancel out, the PQ divide by N respectively. So we will see how this theory can be applied to the development of a control chart for fraction non-conforming. Because the control chart monitors the process fraction non-conforming P. So it is also called the P chart. So this is P chart. This is the P chart. This is a development of operation of the control chart. In chapter 5, we discussed the general statistical principle on which the Shewhart chart is constructed based upon. If the W is considered a statistic that measures a quality characteristic or CTQ on the language of the DMARC, if the mean of the W is the mu subscript W, and the variance of the W is denoted by sigma squared subscript W, then the general model for Shewhart control chart can be represented as the mean plus L magnitude times the standard deviation, and the mean minus L magnitude of the standard deviation. So fraction non-conforming control chart, that is P chart, as a standard value is given, the P plus the 3 standard deviation, and the mean minus 3 standard deviation. So depending on the value of P and N, sometimes the lower bound, it could be less than or equal to 0. If this is the case, it's present. In this cases, customer really set up the lower control limit enforced at least at 0, and assume that the control chart only has an upper control limit and the lower bound going to be 0. So computing the sample fraction non-conforming P hat and plotting the statistical P on the control chart on the chart. As long as the P remains within the control limits and the sequence of the plotted point or plotted sample point does not exhibit any systematic non-randomness patterns. We also would like to see the sequentially increasing and continuous decreasing pattern, which we will consider a different type of, another type of non-randomness pattern. Or a non-random pattern is exhibit in the plotted point that can be observed. We can conclude that process fraction non-conforming has most likely shifted to a different value. Now, sometimes if it shift down, that will be okay, the quality improve. However, sometimes it goes up to a higher level, then they draw our further attention. When the process fraction non-conforming P is not known, then it must be estimated for sure from the observed data. The usual procedure is to select the historical data based upon the n preliminary samples, each of which with a sample size n. As a general rule, n should be at least 20 or 25. So this we require is at least 20 or 25. This is quite moderately and quite large sample sizes. Then if there are DI non-conforming units found in sample I, we compute the fraction non-conforming in the I sample as follow. Pi hat equal to the DI divided by n, I starting from 1, 2, 3 until n. And the average of this individual sample fractions non-conforming is available. So we take the average of that and denote by P bar, summation DI, and divide by n. N is the number of sample, n is the sample size for each sample point. So the statistic P bar estimate the unknown fraction non-conforming P. So the center line and the control limit of control chart P can be computed as follows, like a P bar, 3 standard deviation, and since the P is unknown, should be replaced by P bar. And this is center line, this is the mean, subtract the 3 standard deviation. So as noted previously, this control chart, also often called the P chart. So this is an example. So this is the frozen orange juice concentrate. This is like the mini. Okay, this appears to be a false alarm. So yeah, don't pay attention to that. We are lucky enough. There's not a fire alarm. So like a minute May, the mini May in Taiwan. So you go to the supermarket. You're going to buy a juice concentrate, a pack of 6-ounce cardboard canes. These canes are formed on a machine by spinning them from cardboard stock and attaching a metal bottom panel. And by inspection of a cane, we may determine whether when filled, it could possibly leak either on the side seam or around the bottom joint. Such a non-conforming can has an improper seal on either side seam or the bottom panel. So then before we like to fill the juice inside, we're going to test if there's any leaking on the side seam or the bottom of the panel. So to establish the control chart, 30 sample of sample size 50 each were selected at half an hour interval over a 3-shift period, is 24 hours a day, in which the machine was continuous operation. The data are shown in table 7.1, like here. So we construct a phase 1 control chart. That means we're going to collect the preliminary data. The purpose of the preliminary, so the phase 1 is to collect the data related, and then we like to construct some parameter, also like to add a parameter and to construct the upper bound and lower bound, the control limit for the phase 1. Then if the process is in control when this data were collected, since the 30 sample contain totally we have 347 defective items, non-conforming case. We find based upon the equation 7.7, P bar is equal to 0.2313. So using P bar as an estimate of the true process fraction non-conforming, then just plug in the standard error of the P hat of the P bar. The P hat, then we can calculate the upper and the lower control limit as so this is a 0.2313 plus and minus 0.1789. So the fraction non-conforming will, well, between the 40% and the 5%, is quite high, like here. So this 41. So this is 4. So yeah, the total of 40. So the center will be around 23%. The above upper and the lower control limit shown in the figure 7.1. The sample fraction non-conforming from each preliminary sample is plotted on the chart. We know that the 2 points, particular, those corresponding to sample 15 and 23 above the upper control limits, so that the process is considered not in the control status. So this point must be investigated further to see any assignable causes can be found or determined, and the corrective action should be taken. So like this. So analyze the data about the sample 15 indicates that a new batch of cardboard stock was put into production during the half-hour period. Yeah, we found there's a assignable cause. The introduction of new batches of raw materials sometimes causes irregular production performance, and it is reasonable to believe that this has occurred here. Furthermore, during the half an hour period in which and the sample 23rd was obtained, a relatively inexperienced operator has been temporarily assigned to that machine. That's what it accidentally happened. And this could account for a high fraction non-conforming obtained from that sample. So yeah, this is assumption. We assume this is a new vendor, this is a new operator. Consequently, samples 15 and 23 are eliminated since assignable causes are identified. So those two data cannot be taken into consideration. And the new center line and the revised control limits can be recalculated as follow. So that will fall in within an interval of the upper, the 39%, lower about the 4%. The revised center line and the control limits are shown in the control chart in figure 7.2. You can see that 7.2 revised new operator. Yes. So know that we have not dropped sample. So even though 50-50, so the revised center line limit are shown in the control chart in figure 7.2. Note that we have not dropped the sample from the chart, but they have been excluded from the control limit calculation. We have noted this direct on the notice is directly reflected on the control chart. So this annotation of the control chart is to indicate unusual points. So process adjustment or title investigation made a particular point in time for a useful record for future process analysis should become a standard practice in control chart usage for the future. So this is a new operator, so we readjusted, and yeah, okay. So sometimes it's a 1 point, just extrapolate as well. So sometimes it has happened here. And also note that the fraction non-conforming from sample 21 now exceed the upper control limits. However, analysis of data does not produce any reasonable or logical assignment causes for this. Wow, so strange. Sometimes it happened. We decide to retain that point. Therefore, we conclude that the new control limit shown in the figure 7.2 can be used in the subsequent period of time for future samples. So we have concluded that the control limit estimation phase 1 of the control chart usage now has been done. So okay, there's a further continuation of the calculation of the sample information following the table 7.1, starting the sample number starting from the 31 until the 54. So wow, this is a drop since I think the process improvement had been done. So okay, the P has been dropped below to the 11%. So from the process fraction of computed preliminary data, using the procedure given in section 4.3.4, then the hypotheses are like P1 equal P2 since the duty have process been improved. They equal or equally well in performance. P1, the process fractional non-conforming for the preliminary data. P2 is a process fractional non-conforming in the current period. So yeah, conduct some the comparison. So approximately, finally, the Z value is quite high, so we reject the null hypothesis. Then figure 7.4 show the control chart with these new parameters. Note that since a recalculated lower control limit is less than 0, we set it back to 0. Therefore, the new control chart we'll have only upper control limit from inspection, the figure 7.4, like here. 7.4, yeah, machine. So we do some machine adjustment. Yeah, like here. We see all the points will fall inside the revised control limit. Therefore, we conclude that the process is in control once again at the new level after the process adjustment. The continued operation of this process chart for the next 5 shifts is shown in the figure 7.5. It's 7.4, yeah, 7.5. Yeah, it's going further. That's great. So data for the process during that period is shown in the table 7.3. The control chart does not indicate lack of control. Despite the improvement in yield following the engineering changes in the process, do some adjustment in the introduction or control chart. The control fallout of P bar down to 11% is still too high. The further analysis and action should be required to improve the yield as well. This management interventions might be further adjustment to the machine, statistical design experiment, known as the DOX or DOE, going to refer to the part 4 in this textbook, are an appropriate way to determine which machine parameters are critical to further process improvement, and then the appropriate magnitude of and direction of this adjustment, the control chart should be continued during the period in which adjustments are made already by marking the time scale of the control chart. When a process change is happening, then the control chart becomes a logbook. So like a system log in which the timing of the process intervention and the subsequent effect on process performance arising from the machine adjustment can be easily seen. And this log aspect of control chart usage is extremely important for the daily QA and incoming QA or in-process QA. So design of fraction non-conforming chart, this is also known as an economic design. The 3 parameters must be specified in advance. First one, the sample size. Second, how often you collect the sample. The width of the control limit, how wide. You're going to get wider more to be more conservative, or you get a more compact to be more sensitive in order to enhance the power or detectability. The common to base chart on 100% inspection of the all process output over time. So sometimes it is not a usual practice since for nowadays the production practice is quite with a high variety and small batches. So sometimes the inspection of the 100% over time is not a wise choice. So rational subgroups may also play important role in determining sampling frequency. So how large of the sample of the subgroup should be formed. Interpretation of points on the control chart for fraction non-conforming. Example 7.1 illustrates how points that plot beyond the control limit are treated both in establishing the control chart and during its routine operations. Care must be exercised, must be paid in interpreting points that plot below the lower control limit. If it's plot below lower, don't worry about that too much. This point often do not represent a real improvement in process quality. Sometimes it does not reflect in that sense. This point often does not represent a real improvement. And what does it improve? Frequently, they are caused by error in the inspection process resulting from inadequately trained or inexperienced inspectors or operator, or from improperly calibrated test equipment or inspection equipment. So we have also seen cases in which the inspectors, the inspector on purpose pass non-conforming unit or report of fictitious data. So the analyst must keep this warning in mind when looking for some assignable causes if the point plot below the lower control limit. So it might be an error or might be a mix of the 2 different products. Know that the downward shift in P are attributable to improved quality. Once it goes down, it's a good. However, we still need to understand what is root cause, what is a possible cause behind, or a sign of causes behind, or nothing happened. However, you just mistakenly mixed up the 2 different output of the process. So next, we're going to move to the NP chart. So this is the number of the non-conforming based on the number of the non-conforming items. This is NP 3 standard deviation MPQ, NP minus 3 MPQ. Hold on, let me have a fill the cup of water. So if a standard value of P is unavailable, then P bar must be used to estimate P. So we need to estimate for the unknown parameter P. Many non-statistically trained personnel might find NP much easier to interpret than the usual fraction non-conforming control chart. So NP will be much more preferred by the practitioners. So variable sample sizes in some application of the control chart for fraction non-conforming, the sample is a 100 inspection of the process output over some period of time. So yeah, the 100% inspection for the fraction non-conforming. So we need to inspect all the sample, then the P can be computed. Since a different number of units could be produced in each period, so control chart will have a time varying sample sizes. There are 3 approaches that to deal with, such as non-uniformity in sample sizes, to constructing and operating a control chart with a variable sample size. First one, variable width control chart, and the first, perhaps the most simple and directly immediate measure is to determine the control chart, control limit for each individual sample that are based on the specific sample size. So that is to say, if the I sample is of sample of size Ni, then the upper and lower control limit can become the P bar plus and minus 3 standard deviation, no problem, divided by Ni. Ni is the changes from sample to sample. So the standard deviation will up and down due to the variable samples, the time varying sample sizes. Note that the width of the control limits is inversely proportional to the square root of the sample size. You get a larger sample size, you get a smaller standard error or standard deviation. So the control chart, the control width will become tighter. So this is example, and corresponding to the 25 sample, the purchase order data for a control chart for a fraction non-conforming with variable sample sizes. So we compute each one, the upper control, lower control be up and down, And sometimes it is less than 0, we just force on zero value at least. So you can see on the left, the control chart for fractional non-conforming with a variable sample size. You can see the G-jack seesawing up and down, and standard deviation. Control chart fractional conforming variable sample size using Minitab. So actually, this is the same pattern exhibit when the time varying sample sizes are utilized. So second, average sample size approach. We're going to do the average n bar equal to the 98 and summation Ni divided by 25, and we use a single number of sample size. Then that's it. And then use a single. So exactly one of the points exactly reach the upper control limit for the sample. The third one, standardized control chart. So now standardization going to force the center will be 0, upper will be 3.0, lower going to be the minus 3.0. The third approach to dealing with a variable sample size is 2. Variable size is to use a standardized control chart where the points are plotted in standard, in terms of the scale of the standard deviation unit. Such a control chart has a center line directly on 0, upper and lower at +3 and -3 respectively. So the variable product on the chart can be represented as that, the pi minus the mean divided by standard deviation. So where p or p bar, if no standard is given, the p bar should be used instead, is a process fractional non-conforming in the in-control state. The standard control chart for the purpose of older data is shown in the table 7.4 and the figure 7.9. The calculation associated with the control chart shown in the table 7.5 and test for runs and the pattern recognition method could safely be applied to this chart because the relative changes from one point to another are all expressed in terms of the same unit of the measurement. So it has been standardized. Yep. Okay, then next one is the operating characteristic function and the average run length ARL calculation. The ARL can be classified into two. One is the ARL in, the latter is the ARL out. The operating characteristic, or known as a QC function of the fraction non-conforming control chart, is a graphical display of the probability of incorrectly accepting the null hypothesis. The null hypothesis of the statistical process control, the type 2 error or beta error occurred or committed against a process fractional non-conforming. So the OC curve provides a measure of the sensitivity of the control chart. That is to say, its ability to detect a shift in the process fraction non-conforming from a nominal value p bar to some other value p, and then if the p bar is set up, and so this is something we like to test for different p. What is the corresponding type 2 error that will occur? The probability of the type 2 error for the fraction non-conforming control chart can be computed based upon the beta equal to the p bar less than upper control limit and the p greater than the lower control limit under assumption of the p in the null hypothesis. So can do the D, as long as we like to just represent NP, also can be represented as a D simultaneously, the D less than or NP, the D less than or equal to NP. So these are binomial random variables with parameters and NP. The beta error defined in the equation 7.615 can be obtained from the cumulative binomial distribution table that's attached on the back of this textbook for sure. Know that, and when the lower control limit is negative, the second term on the right of the equation 7.5 should be dropped. So when the lower control limit is, sometimes it's lower than 0, which is not possible. How could the percentage, the representation of percentage is less than 0? It no sense to me. Okay, the table 7.6. So calculation for constructing the OC curve for a control chart for fraction non-conforming with a sample size 50, lower control limit and upper control limit, and P for different P, and then less than 18 and less than 1. So like to calculate the beta, like here. The beta is less than 18 under the some value in the null hypothesis, define the null hypothesis P, and these are less than 1, like here. With sample size, and so this is N, so N is 15 times the lower control limit, 15 times the upper control limit. This is 1, and so 50, this is 1, yeah, sure, 1 point something, okay, less than 18. So probability in this table can be found by evaluating the cumulative CDF of the binomial random variable for small sample less than 0.1. the Poisson approximation can be applied. For large value of the P, the normal approximation can be applied as well. So this is the graph we draw, the operating characteristic curve for the fraction non-conforming control chart when P equal to 0.2. Right here, you can see that, yeah, 0.2. Yeah, the beta is quite. This is almost reached the largest value ever, 0.2. And then, so remaining. So if this more deviate from the center or the average, the trend of the average, and then the beta 2 will be reduced or decreases. So this is a graph. You can just draw this graph by itself. The average run length, ARL, this is ARL1, the reciprocal of the sample point out of the control. So if the process is in control, ARL0, ARL0 is 1 over alpha. Alpha is a false positive rate. It can be considered the false alarm. If it is out of control, ARL out is equal to the 1 minus beta. 1 minus beta is a power, is a probability of the sample plotted out of the control. Since we plotted out of control, that is, we make a correct decision. So this probability alpha and beta can be calculated directly. So they are compromise each other. Then they have a trade-off between alpha and beta. We would like to get a larger alpha, so the beta increases. Now sometimes we got trade-off. So going to increase the alpha, so the control width shrinks. Then we more so if it decreases and type 2 error increases. If type 2 error increases and the type 1 error decreases. So this probability alpha and beta can be calculated directly from the binomial distribution or read it from a QC curve like this. So in the final test, we would like to ask you how to perform the CAN calculation of the type 1 error and type 2 error, ARL in and ARL out. Yes. Okay, to illustrate, consider the control chart for fraction non-conforming using the QC curve calculation in table 6.7.6. So this chart has a parameter n equal 50, upper control, lower control, p bar is approximately 0.20. From table 7.6, the OC curve and figure 7.11, we found that the process in control, then probability of point plotting in control is within, is high to, really high, highly close to 99.73. So in that case, the alpha, the ARL is close to 370, for sure. Yes. Then, therefore, if the process really in control, we will experience a false alarm every 370 samples. This will approximate true in general and Shewhart chart with the 3 sigma limit. The in control ARL is generally considered to be satisfactorily large. And now, suppose that the process shift out of control. Is about 0.3. Table 7.66 indicates that if the p equal to 0.3, if the process out of control to the p, when p like that, and the beta is about 85%, there 1 minus beta, so you approximately need the 7 sample. So we take about 7 sample on average to detect such a small shift with a point the product outside the control limit. So if this is unsatisfactory, then the action should be taken to reduce the out-of-control ARL. Increasing the sample size could be the one, will result in the smaller beta, and then the shorter control, out-of-control run length. Another approach will be to reduce the interval between sample. So going to inspect more samples within a fixed period of time. And that is to say, we currently sample every hour, so we take about 7 hours. So on the average to detect this shift, if we can take the sample every 30 minutes, it will require only 3.5 hours. So the efficiency augmented by 2 times. And on average to detect a shift, another approach is use a control chart that is more responsively or sensitively to small changes, such as accumulated sum or EWMA that will be addressed in chapter 9. Okay, then we stop here and for rest.